Hello, I'm glad to be here again and to talk with you some more about classical test theory. And in this video, I'll be discussing derivations from test theory. To review, there's notation for classical test theory or classical true score theory, which is useful to us. Remember that X is used to denote obtained score or scores on a test, X. T is the true score or scores on test X. E are the error score or scores on test X. And remember also that epsilon there, that E, scripted E or Greek E is the expected value that is the mean of values that we're anticipating. Now there are some variations, a few new symbols that we might want to take a look at. You probably remember sigma squared, or the variance from statistics. The variance, that is, of T is the variance of the true scores. Let's jump down skip one and jump down to rho, which you remember, the population correlation. And there are some variations on rho on the final bullet, which is rho XX X prime, which would be the population correlation between a test X and its parallel test. Rho squared sub xt, the population correlation squared between an obtained score and a true score. And rho, that's the same thing as the first one. Oh no, not quite the same thing as the first one. Just trying to see if you're awake here. Rho xx, the population correlation between an obtained score and an obtained score. Well, all of these expressions are expressions for test reliability. The first one, the correlation between a test and its parallel test, is a designation for reliability. That last one looks like it's a correlation between test scores and themselves, which should be 1, right? But it's read as reliability, and I won't explain more about that in this video, but I may get there at some other point. Let's go back to that K, the second one. The K is the number of items or segments in a test, and this will become important as we go along. Maybe not so much in this video, but later on, but I do want to introduce the idea here. K, the number of items or number of parts that a test is divided into. That's what we mean by segments. So if we divide a test in half, K is 2. If we divide a test into quarters, K is 4. If K is equal to the number of items and it's a 20-item test, K is 20, and so on. Okay. In addition, classical true score theory or classical test theory, you'll recall, is based on 5 mathematical assumptions, including X equals T plus E, and 2 definitions. And we can get an insight as to how we might get a true score from the obtained scores by looking at the following equation, which is also the second assumption of classical test theory, and that is that the expected value here, E, is used to designate the expected value, not the error score. It usually should be pretty clear from the context. I will try to use an epsilon for expected value, but the E is used for the expected value of the obtained scores for a person on a test equals the true score of that person. And this means that it's possible to obtain an estimate of a true score for a person. And recall that we could administer the test multiple times to get this estimate of the true score. Here I have an example of with person 1 who takes a test of whatever and gets scores of 45 and 35 and 42 and 42 and 36. And the odds are, in classical test theory, we typically assume that the person's true level of ability or true level of attitude or whatever has not changed. It's always the same, but rather it's the error which is changing from one test to the other. But you know, administering a test 5 times is awkward. We have to get the person to come back 5 times. There may be practice effects and so forth. So if only we could derive an alternative to this, that would be helpful. And in fact, there are lots of derivations that we can make starting with those 5 assumptions. And I'm going to talk with you about some of those derivations today. We may not get all the way to the derivation that helps us calculate true scores without all of this, 5 times in a row giving the test. but we will get there. By deriving new equations from the assumptions and the definitions of classical test score theory or true score theory, we can obtain new ways of understanding the relationships among obtained, true, and error scores. And some of these new relationships are of considerable practical value. So in the next slides, I'll show you the results of some derivations. I won't show you the derivations themselves, although I will comment on a derivation or two here and there. Those are available elsewhere. They're available in any number of textbooks. Rather, I'm going to focus on the ideas behind these, because they represent important ideas that help us understand how classical test theory looks at tests. They state important relationships. So the first one we'll look at is this one. The expected value of the error scores equals 0. And this rather simple statement helps us understand why, as we take if we take a person and take their obtained score on a test multiple times, it's going to equal the true score, because, well, over time, that error score is going to average out to a 0. Here's a second equation that we'll be using a lot. The variance of the obtained scores, x, equals the variance of the true scores, t, plus the variance of the error scores, e. And although I'm not doing derivations here, I will say that you cannot begin with x equals t plus e in a first step and then get to this equation by simply placing that variance symbol, sigma squared, on top of each letter. If you think about it, you'll realize that violates all kinds of algebraical rules. So rather, it's not a huge distance from those 5 assumptions to this equation, but it takes about a page of steps, or at least I take about a page of steps if I'm trying to derive it, in order to get from x equals t plus e to the variance of the obtained scores equals the variance of the true scores plus the variance of the error scores. I'll just mention that in passing. Here's one. The squared population correlation between the obtained scores and the true scores on a test is equal to the variance of the true scores divided by the variance of the obtained scores. And I want to say that one other way. It's also the case that value on the left, that term on the left, is reliability. So we can also say that the reliability equals the ratio of the variance of the true scores to the variance of the obtained scores. Another one. The squared population correlation, or reliability, between the obtained and the true scores on a test equals 1 minus the variance of the error scores divided by the variance of the obtained scores. And here's another. The variance of the obtained scores on test x equals the variance of the scores on its parallel test, x prime. Remember that x prime represents obtained scores on a parallel test. Here's yet another. The population correlation between scores on test x and test y equals the population correlation between the parallel test of x and y. So if we have a test x, and let's say it's a test of extroversion, and it predicts risk-taking with a correlation of 0.3, and then we substitute for our test of extroversion, a test of extroversion prime, that is a parallel to the test x. That's also going to correlate 0.3 with risk-taking, so long as the tests are so long as x and x prime are parallel. Oh, here's another. The variance of the true scores on a test can be thought of as the number of units k squared of change in the length times the variance of the true scores on a shorter test y. I'm just showing you this. We're really not going to be using this in class very much, but I'm showing it to you because it's a fundamental part of test theory. And what it says is that basically true score variance, which is the good kind of variance we're looking for, that is to say the measurement of the person's actual quality, increases by the square of the test length. Now this is important because the obtained scores variance also increases, but not by k squared, just by k. And if you didn't follow that, the bottom line, which is really all you need to know for this class, is that the longer the test, the higher its reliability. Other things being equal, assuming all the items function in the same way, the longer the test, the higher reliability. And this is the equation. This is one of the equations that tells us that. Here's another one. The population correlation between a test and its parallel test is equal to the variance of the true score over the variance of the obtained score. And alternatively, once again, there are multiple ways sometimes of reading these formulae. The reliability between a test and its parallel test is equal to the ratio of the true scores to the obtained scores. Here, I think we have lost a minus sign, but it's the population squared between the obtained and the true scores in the test are equal to 1 minus, that should be, 1 minus the variance of the error scores on the test divided by the variance of the obtained scores. Or put another way, a test's reliability is equal to 1 minus the ratio of the error score variance to the obtained score variance. And that tests there should be possessive. It should be apostrophe S. So by using the fundamentals of classical test theory, the 5 assumptions and 2 definitions, psychometricians have been able to derive a number of further relationships among test scores, variances, and correlations. A number of the important relationships have been depicted in this video, though there are many more. But these derivations will become important to applying the theory to the construction of tests, and particularly to the concept of reliability. Thank you for watching this video, and if you have any questions or comments about it, please let me know. Thank you.